Hello, everyone. I'm Zohreh Davoudi from the University of Maryland. This is the third lecture on the topic of finite volume formalism for Lattice QCD as part of the Lattice Gauge Theory for High-Energy Physics traineeship course. So in the previous two lectures, we've learned how to deal with finite volume effects in the single hadron sector, whether we put QED or QCD in a finite volume. Today, we're going to extend that discussion to multi-hadron sector, in particular, two-hadron sector. I'm going to just focus on QCD finite volume effects for the sake of this lecture. So here is an outline of what we're going to learn in this lecture. First, we're going to talk about the 2-to-2 elastic scattering and Lucher's formalism. I'll introduce the formalism and give you a qualitative picture of its ingredients first. I'll give you a simple derivation based on quantum field theory of this formula. We'll talk about extensions to multi-channel 2-to-2 scattering. We'll talk about how we can derive information about bounded states and resonances from this finite volume formalism. And then finally, I'll talk about recent extensions and applications of this finite volume technology. All right, so let's see why we are interested in developing a finite volume formalism after all. All right, so as we saw, it was very important to quantify finite volume corrections to observables in single hadron sector, all the way from the masses, magnetic moments, and so on. But as I said, finite volume corrections are not the only reason that we care about developing finite volume technologies for quantum field theories. Let's see and understand why. All right, so remember that we perform our lattice QCD calculations at the moment using a Euclidean space-time signature, okay? It turned out that we can essentially continue or analytically continue these correlation functions to Minkowski space in principle. And by in principle, I mean if I really had access to a continuous function. Unfortunately, with lattice QCD computations, we first of all evaluate these correlation functions in time at discrete set of space-time points. Further than that, we also have finite statistics, right? So we have uncertainties on these measurements of these correlation functions. So despite the fact that there's this important theorem in quantum field theory, if our theories are reflection positive, we should be able to analytically continue them. In reality, we don't really have access to these functions in Euclidean space-time, but rather snapshots at discrete set of values, okay? So it turned out that for certain observables, that's not an issue. For example, if we're interested in single hadron energies or multi-hadron energies, these quantities can be already read off from Euclidean correlation functions. They're kind of insensitive to the signature of a space-time. So what about some observables that are sensitive to the signature of a space-time? We'll consider a scattering amplitude, something that is a truly dynamical process, in a sense that you have to define your asymptotic states, scattering states, far in the past and far in the future. You have these hadronic wave packets that don't interact. And as they evolve in time, you turn on the interactions. At some point, they start to interact with each other, scatter off each other. And then far in the future, we will measure scattering amplitudes on an S matrix. So already at the heart of the definition of an S matrix is really the notion of time evolution and time signature, okay? In particular, if you're in Euclidean space-time, you can't really define these asymptotic states, okay? So it turned out that there is an important theorem called Majonian test on no-go theorem that unfortunately would tell us that it is impossible to learn something about, for example, elastic scattering of two hadrons by just accessing Euclidean correlation functions unless we're at kinematic thresholds, okay? And this statement is only valid for correlation functions that are calculated numerically and also in infinite volume, okay? So that's the caveat, right? If it would have been just that, we would have not been able to access any scattering observables from these Euclidean calculations. But it turned out that we can invoke the fact that we are performing calculations in a finite volume, not infinite volume. We can escape this no-go theorem. And this is something that was advocated for and developed by Martin Lushers in late 80s, in fact. And there's been identical or similar quantum mechanical settings for the same problem, accessing scattering phase shifts from finite volume energies that was developed before that, but really in the context of lattice QCD quantum field theories is really in late 80s where when Martin Lusher proposed that we can use these finite volume technologies to get access to Minkowski S matrices out of Euclidean correlation functions. Okay. So why is that the case? I mean, this is a very strong statement that only by accessing a set of, in fact, finite volume energies, it turned out, we can learn something about Minkowski amplitudes. And the underlying reason for this is that, and this is something that is valid for interactions that are finite range, essentially. So if you give me some interactions that I can fit it inside a volume, then when it comes to ace matrices that are information about asymptotic states, then we're really dealing with the IR physics, right? So the short range information or interactions are exactly the same interactions that would cause the finite volume energies inside a volume to be different from infinite volume energies. And they're exactly the reason that we get the scattering in infinite volume, right? So as long as we're not distorting the interactions in a finite volume, as long as our volume is large enough such that we can contain the interactions inside the volume, then we can deduce information about their scattering S matrix, the asymptotic S matrices, from information on how these interactions actually affect quantities in a finite volume, because they're exactly the same interactions in finite and infinite volume. That's really sort of at the heart of why something like Lusher's formalism can work. I also show you what the limitations of Lusher's formalism is. If you have interactions that are long range, then you have to rethink all this formalism, okay? So this is really qualitatively why something like Lusher's formalism can come to help us to get a scattering S matrices, okay? So this notion would become far more clear as we go through a derivation. So let's do that. Let's look at the derivation based on a quantum field theory. So Lusher's derivations were in there, his papers in 80s and early 90s. But then there was this other nice papers that came along and showed even more simplified pictures of those derivations using the standard quantum field theory or perturbation theory calculations, both in the context of relativistic quantum field theories, also in the context of non-relativistic effective field theories. Okay, so let's just start this. Let's try to see how we can get a connection between finite volume energy eigenvalues that we get out of in Euclidean calculations in principle and a scattering amplitude for a 2-2-2 process. Okay, so what we're going to do is we're going to look at let me get so we're going to look at again a cubic volume with periodic boundary conditions, and we start by defining something that I call a finite volume amplitude. All right, so amplitudes, as I said, are not well-defined objects in a finite volume because we really need an infinite volume to be defining this asymptotic states so far from each other. Nonetheless, it's a useful object to still define. Alternatively, I could start from a correlation function, which is more well-defined in a finite volume, right? I can create and annihilate my states, and I can look at the propagation as a function of essentially Euclidean time in a space. But you can also truncate them and define this object finite volume amplitude. For all purposes, the pole structure of these amplitudes and correlation functions are going to be the same. And because I'm interested in the singularities of this object, in the end of the day, I can define this amplitude instead of a correlation function. And I'll tell you what the form of this amplitude is in the next page, okay? So again, I'm interested in the scattering of two hadrons. Let me get rid of these lines. Okay, so we're interested in the scattering of two hadrons. And for all purposes, I don't have to think about quark and gluon degrees of freedom. Again, the same arguments that we made for single hadron observables, and when it comes to finite volume effects. If you're trying to identify those finite volume effects, we're thinking about IR physics. IR physics is described by asymptotic states of the theory, which are rather hadrons as opposed to quarks and gluons. Okay, so by the two lines that I have here, I mean two hadrons that are scattering off each other, okay, in a finite volume. So that's what the superscript V corresponds to. We are in a finite volume with periodic boundary condition. And I'm going to assume that the time is infinite. I'm going to assume that space and time are continuous. So we're not going to deal with discretization effects and all sort of other effects, and just like really isolating the effect of a special finite volume. All right. Okay, so again, we're interested in finite volume physics. We can start with our hadrons and we can ask, what kind of contributions do I expect in some sort of finite volume amplitude? And there is a counterpart for this in infinite volume. So you can always think about the counterpart in infinite volume, write down all the diagrams or a skeleton expansion of your amplitude. And then you can then assign the same amplitudes with modifications in terms of their finite versus discrete sums in the loops, and then call it a finite volume amplitude. That's all I mean by this. Okay, so let's see what kind of diagrams would contribute. Okay, I have two hadrons. They can scatter by something that I call a beta salpeter kernel. Okay, and I'll tell you in a moment what contributions I'm expecting to put into this kernel. Then you can have a geometric sum, essentially, that consists of multiple insertions of these kernels, right? So I can have these particles to scatter with the single kernel, and then these two particles would propagate for some time. They would scatter off each other, and then so on and so forth, right? If I tell you what contributions are in K, then I can claim that this is the full expansion of the amplitude to all orders. So what contributions are in this kernel as a salpeter kernel? Well, it could be just the leading order contribution. Of course, it depends on the theory. You have to give me a Lagrangian. I have to identify the Feynman rules associated with all the interactions of these hadrons in that Lagrangian. For the sake of this derivation, it turned out that we don't have to worry about that. This is a very generic derivation. It doesn't require you to identify what contributions are there, as long as you just look at several generic properties of these functions, okay? So let's say I'm in a theory where I can have a contact interactions between these two hadrons, like in nucleons. We can have nucleon-nucleon contact interactions. Or I could have a theory when these two hadrons can exchange another particle. Like in nucleon-nucleon scattering, we can have a pion that is exchanged between these nucleons. Or maybe they can exchange the same type of particles. Or maybe they can exchange two types of the same particles. Maybe I have a theory when I have 2 to 3 vertices of the same type of particles, and eventually I get a contribution to my 2 to 2 amplitude. So as you can see, I'm putting everything that first of all is connected, all right? And second of all, does not include what I call S-channel loops. These S-channel loops are the ones that I have only two particles propagating, like so, in an S-channel. Because I've already put all those S-channel contributions in this expansion, I don't have to really then worry about it in this expansion. So everything else except for two particles in the S-channel are going to be inside this kernel. Of course, they could still be an S-channel, but there are 3 particles S-channel in this form, okay? All right, so we talked about our finite volume amplitude. We talked about contributions to this S-channel 222 beta salpeter kernel over here. And now you may ask, why am I separating the S-channel loops from everything else? What's the idea behind doing a skeleton expansion that looks like this as opposed to something else? All right. So there's one reason for this. I'm going to look at 222 scattering processes that are elastic, okay? Meaning that I don't have enough energy in the process to generate a third particle or a fourth particle and so on, okay? So what that means is that although I may be able to generate these particles in intermediate states because they could be off shell, they don't have to be on shell, I cannot introduce on shell third particle, okay? So all I can do with the energy that is available in the process is to put at most 2 particles on shell in intermediate state, but no more than that. And you see one aspect of all these diagrams is that if I draw a line here, that means that I have to have enough energy to put 3 particles on shell if I want to do that in this case. The same here, the same here is even like more, that's 4, and then the same here. So for all things that happen like in intermediate states, I will have a situation where there is a third or fourth particle that can go off shell, but not on shell, okay? However, in S-channel diagrams, 2 particle S-channel diagrams, I can actually put these 2 particles on shell, okay? So that's why I did this separation of S-channels versus everything else. So with this distinction, it turned out that this finite volume kernel happens to be exponentially close to this infinite volume counterpart. I think this is something that I'll talk about, yes, in the next page. So let's not talk about it right now. Okay. So what else? What are these objects that I've defined, these propagators? Well, you can also imagine that there is a perturbative expansion to all orders for this propagator, this full propagator of the hadrons. It could be the bare propagator. It could be a self-energy contribution that looks like this. Depending on the theory, it might have a contribution that looks like this. Again, depending on the theory, there may be a third particle that looks like this. And again, as you can see, if I try to draw a line somewhere in these diagrams that doesn't include this initial and final states only, then I'm dealing with a situation that I have more than 2 particles that need to go on shell. Okay, so in that regard, they look very similar in their structure or kinematic structure to the ones that I draw here for the kernel. All right. So that's all the ingredients. So my amplitude has these full propagators that I have defined by this perturbative expansion over here to all orders, so it's complete. And then these kernel functions, which are the S-channel 222 beta salpeter kernels with the following expansion to all orders. Depending what your theory is, you may or may not have different contributions here, okay? All right, so let's go to the next page and state a few important points. Let me get rid of these. Okay, so the first point is the fact that, as I said, we're below inelastic threshold, right? So we're just doing 222 elastic scattering. It turned out that below inelastic threshold, this kernel K can be replaced by its infinite volume counterpart up to only exponentially small corrections that go like e to the minus m pi L or ml, where m is the mass of the lightest hadron relevant to the process. Most QCD processes is going to be a pion, okay? And so that means that I can take the finite volume kernel and just replace it by infinite volume kernel up to exponentially small corrections that I'm going to, by the way, ignore for the rest of this lecture, which might sound inconsistent with what we did in the previous lecture because we really try to identify these finite volume corrections to the masses and so on that are exponential. But for the sake of this lecture, we're worrying about a much larger finite volume effect, which is power law, okay? So as long as we have large enough volume that these corrections are a small percent level, sub-percent level, we can just completely ignore them, or even we can characterize them if we have a right effective field theory. But then at that point, we introduce some model dependence into the picture. Anyway, so for the sake of this lecture, we're not interested in these exponential corrections. I'm trying to identify something that is larger in magnitude and more important for the construction, as we will see. What about these fully dressed propagators that I talked about? They're contributing to the finite volume amplitude. Again, the same story. If I'm below an elastic threshold for producing a third or more particle, then I can replace this full propagator with its infinite volume counterpart up to exponentially small corrections. And the reason for this, as we will see, is the fact that when we try to replace a finite sum with an infinite integral, okay, as long as the integrand or the summand is regular function of the kinematic that I'm integrating over or summing over, then I can always replace the finite infinite volume piece up to exponentially small differences, okay? And this is obvious kind of from Poisson resummation formula. I remind you of the calculations that we did for the mass of the single hadrons, and we saw that we had to resort to Poisson resummation formula that would allow us to identify the infinite volume piece plus the finite volume piece. And in order to work out the finite volume piece, we had to look at the pole structure of our summand. And because the poles were located not on the real axis, but on the imaginary axis, it allowed us to take the integral and come up with exponentially suppressed forms. Now, let's just generalize this to any other summands, any other loop integrations that we replace with the summations. As long as our kinematics does not allow us to have real poles, real singularities, then we're dealing with exponentially suppressed contributions that we can identify, okay? So it turned out that for the kernel and the propagator, that's really the case. Because as I said, these guys, if I put a line over here or over here, it turned out that, and then also like here, and we worked out what the finite volume compared to the infinite volume contribution is. We always see that because we can't really put a third particle on shell, we're dealing with off-shell kinematics, and these off-shell particles cannot really propagate far. They're not on shell, they cannot propagate far, they're limited to a finite range, and therefore that gives you an exponential correction. So you can intuitively understand it from a picture of off-shellness. You can also mathematically understand it from this Poisson resummation trick that we have seen before, okay? All right, so what else should we know? So what that means is that we're trying to then characterize only the large or power law finite volume corrections. And therefore, let me go to the next page. We have to only focus on diagrams that would give us two particle intermediate states that can go on shell. And those are just the S-channel diagrams. So remember in the expansion of the infinite volume V, let me show you this. I said that only these S-channel loops can give on-shell conditions for the kinematics that we're interested in. So that's why we did this separation, essentially. We separated contributions that would give us power law volume corrections from the ones that would essentially give you exponential corrections that we can ignore for the rest of this calculation. Okay, so that was the reason for doing this particular skeleton expansion as opposed to something else. All right. So what is the difference then between finite and infinite volume quantities in this picture? Well, just give me the loop, these S-channel loops, which is a finite volume sum over some single momentum. I can replace it with an infinite volume integral over continuous variable and a contribution that is purely finite volume that we're trying to characterize, okay? So that would be the notation for the rest of the derivation. Any S-channel loop is replaced by an infinite volume counterpart and a piece that is purely finite volume correction, and it's supposed to be, by the way, power law. Why is that? Because as we said, the only time that we don't get exponential, rather power law correction, is that when these two particles go unshelled. So this notation is to show that these two particles are unshelled. And these unshelled particles can, as we will see, give us the power law corrections. And by unshelled, it means that they can propagate freely, right? So they can go and see the boundary, and therefore their momenta would be like 2 pi over L. And that's why we see sort of power law corrections. All right, so then how can we analyze this? How can I actually learn the form of this function? So let's just look at the generic function, S-channel loop function. I'm going to call it the GV. So the guy that I have over here, if I have two kernels associated with the left and right, which is this diagram that I have over here, I have two of these kernels on the left and right, and I have my S-channel diagram. All right. So it's going to be a function of the kinematic variables P and P prime. What are the P and P prime? They are either the total momentum associated with the initial or the final state. Okay, so sorry, these are the relative momenta. So the total momentum is fixed, right? Elastic scattering, conservation of momentum, total momentum of the two particles P1 and P2 is fixed, and therefore it's going to be equal to P1 plus P2. And this is the form momentum, both energy and momentum, right? So that's in terms of the kinematics. So if we're dealing with elastic scattering, we have two particles initial state that go to two particles final states, energy is conserved, and we don't introduce any third particles and so on. Okay, so that's that notion of elastic scattering. Okay, so now let's look at the structure of this G of V. Again, it's that there are two kernels that would depend on the relative momentum P and the relative momentum P prime of the initial and final pairs. So P1 minus P2 and P1 prime minus P2 prime. And then they would also depend on the momentum in the loop, which in this context, again, is this relative momenta, because I'm writing this as Q and Q minus P, where P is the total momentum of the process, okay? So that's, therefore, we're assuming that the kernel doesn't depend on the total momentum of the system, which is a good assumption because everything is going to be sort of translation invariant and so on. So it only depends on these relative momenta. So then we just write down what this expression for the propagators are, and that gives us the function for the loop momenta, right? So I have two propagators, and let's assume that these are scalar particles, no spins, and they have mass m1 and m2. Okay, so I have q minus p squared minus m1 squared plus I epsilon, q2 squared minus m2 squared plus I epsilon. And you see I'm in Minkowski space. As I said, the pole structure of these correlation functions don't depend on whether I'm in Minkowski or Euclidean. So you can either do your loop integrations in Minkowski or Euclidean, but you have to kind of keep track of their relation to each other in the end. So let's just stick to the Minkowski for this consideration. Okay, so then there is an integration in principle over this, but because we're in finite volume, there is actually V here, according to this notation. That means that I have still an integral over Q0, the zeroth component of the loop momentum, but the integration is replaced by 1 over L cubed sum over discrete values of momenta, where momenta are 2 pi over L times this integer n vector, as we've seen in the previous lectures. Okay, So this is the function, and now we have to process it to be able to write it as something that is only an infinite volume contribution, meaning that everything is replaced by an integral over continuous variables and the rest. So let's see how we can do this. All right. And I should tell you that this psi factor over here is a symmetry factor. So I have given what the value is. It is 1/2 if the two hadrons are identical, and it's equal to 1 otherwise. Okay, so this usual symmetry factor for these Feynman diagrams. And some things about the kinematics, I want everyone to get comfortable with sort of processing this kinematic variables. So in the previous page, I have everything written in the lab frame, right? So that's why I have this total momentum P, which could be non-zero. But sometimes you're interested in center of mass frame. In the center of mass frame, obviously, we can relate the energy of the center of mass frame, E star, to the energy of the lab frame by the following relation, where P is, again, the total momentum of the system. It also implies that, it also means that I don't have to worry about the relativistic versus non-relativistic relations. Obviously, in this form, I have relativistic propagators. And if you have relativistic kinematics, you also have a relation between the E and E star. This is given by gamma, which is not necessarily equal to 1. And you have to account for that factor. Okay, so the first exercise for this lecture is about deriving what the relative momentum in the center of mass is. Usually when you think about this, when the two particles have the same mass, it's kind of easy to deduce what the relative momentum is in the center of mass. So, and it is a simple exercise, but I want everyone to be able to derive this relation for the relative momentum out of the energy in the center of mass and in terms of the masses of these objects. And then you can justify that this recovers the right limit when M1 is equal to M2, because sometimes you're going to need this relation to relate quantities once you process these relations. Okay, so now let's try to process that finite volume integral or sum, that finite volume summations, and see what the relation between that sum and the corresponding integral could be. Let me get rid of this bit. Okay, so as I said, if I want to do the Poisson summation formula, like, well, the first thing that we have to do is to take the QCD integration. And the next thing that is left to do is to do the summation. And once we do the summation, we can use the Poisson resummation again, replace this with an integral and the remaining sum. And in the remaining sum, the only way to get non-exponential corrections out of that sum is when the two particles can go on shell. And we want to identify that piece, okay? Which means that M1 squared should be equal to Q minus P squared, and Q squared should be equal to M2 squared. That's really the unshell condition. That's when this bit is actually singular, right? That's what I mean by unshell condition. The two particles are on their mass shell, okay? So with this unshell kinematics, the value of the relative momentum in the center of mass Q star would be essentially equal to the P star and P prime star, right? So in terms of the magnitude of the momentum, there is only one thing in the problem, and that's already being set by the total energy and momentum that is given to us in the process, right? So what is unfixed in this scenario is really the angular dependence, or the between the P1 and P2 particles, right? Or in the center of mass frame, between the direction of the initial incoming particles and the final outgoing particles, right? That's the only directionality that is unfixed. All the magnitudes are fixed because this is an elastic process, and energy momentum conservation will give you all the values of the magnitudes of these objects. Okay, so that's the only thing that is unfixed. That means that in terms of these angular variables, I can go ahead and decompose these functions into a set of partial waves, right? Anytime I have a function of some angular variables, I can think about the partial wave decomposition, okay? So that's what I mean by this. I get the delta GV function, which is a function of these kinematics P and P prime, right? And then I write it in certain terms of a matrix now. A matrix in Lm and L prime M prime quantum numbers. Lm would characterize the directionality of the initial particles, right? And that means that sort of the directionality associated with the two incoming particles, P1 and P2. L prime M prime would be associated with the directionality of the two final particles, right? And because of the conservation of angular momentum in infinite volume, we would have expected this to be a diagonal matrix, right? Your scattering amplitude should be a diagonal matrix because of the conservation of angular momentum. However, remember, we are in a finite volume, okay? That means that we have cubic symmetries, not full rotational symmetry. And that means that we can have off-diagonal contributions to this object. So don't be surprised to see a form where off-diagonal contributions don't vanish. This is expected. We are breaking rotational invariance in this picture. Anyway, so this matrix in Lm, L prime, L prime, and prime bases, which is essentially defined as GV minus G infinity, just a finite volume corrections to that sum that I wrote before, can be written in the following: minus I times the kernels associated with Lm, some internal L1, M1, some delta GV of L1, M1, L2, M2, and then the kernel L2, M2, L prime, M prime. Okay, so all I've done is, and there are a few lines of algebra, so don't try to do this in your head. But what I've done is that, well, first of all, we're in the unshelled kinematics. Second of all, this K and K, the two kernels as a function of different kinematics, can be separated into two kind of vectors on either end, or two matrices on either end. And the remaining matrix would be something that would not depend on the kernel and should be also decomposed into partial waves. Okay, so that's the notation. Okay, so let's look at this. So now I claim that the form of this partial wave decomposed delta GV that I have in the this curly GV that I have in the middle is given as following. And the first term is just the diagonal part. This would have been the part that would occur in infinite volume 2, right? So this is like the diagonal part. And the prefactor are in terms of this center of mass kinematics, okay? The second term, in principle, can have contributions to the off-diagonal piece, and it's given in terms of this integral over 3 of these y-element functions, okay? And not only that, it has also the dependence on what I call a finite volume function, or a Lucher's z function, called as C, depends on the total momentum of the system, and it has the L and M sub indices or subscripts. And it's given by the following for the fully relativistic kinematics. I have to say that this P looks very similar to the total momentum, but it is not total momentum. So this P means the principal value of the integral, okay? Because the integral in principle can have singularities, right? So this is the well-defined way of defining in a regularized integral with this principal value. And that's what it's given in the definition of this object. So this object then depends on the sum minus integral of a function that looks like 1 over k squared minus p star squared. K star is the variable that we are integrating over, and it's given in the following form, written in terms of the k that is being integrated over the parallel component to the total momentum and the perpendicular component to the total momentum. And gamma is your relativistic factor. Alpha is defined in the following: if M1 is equal to M2, it's just 1/2. Otherwise, it has this following form. And the rest, I think, is self-explanatory. Okay. All right, that sounds like a very non-trivial relation. And therefore, there's this bonus exercise here, and there's not enough time to actually show you the full derivation. Nonetheless, the full derivation is given in this reference, this very nice reference from 2005, where they present this particular derivation that I'm going through using the effective field theory skeleton expansion of the amplitude or correlation functions, and have some details about how this relation can be derived. I would encourage you to just like try to do it yourself before consulting the reference, because it's kind of a very good practice of your math skills and understanding kinematics and partial wave expansions and so on. It's a fun exercise, but it might take a little bit to really get every factor right. All right. Okay, so all we have done so far is just think about this delta GV function and write it in terms of an infinite volume bit and a bit that is purely finite volume evaluated on shell, because that's the only piece that gives us power law corrections. We're not interested in the exponential corrections. We just ignore them. And that's it. So far, that's all we've done, but we're not quite done. Okay. Now we have to see how we can process this into an amplitude, finite volume amplitude. Okay. So if you remember the skeleton expansion of the finite volume amplitude that I mentioned before, maybe I'll show you again so that you can remember what we're talking about. It was a while back. Okay, so I'm going back to all the way to this relation, which was an expansion of these kernels repeated multiple times to all orders in these S-channel loops. I told you that the K can be replaced by K infinity, and KV can be replaced by K infinity. I told you that these S-channel loops that are coming with their Ks in the left and right can be expanded in terms of a finite volume piece and an infinite volume piece in a partial wave base. Okay, so now let's put it together. So if we put it together, we'll see that, well, the first term is going to give you a minus ik. And by k, I mean k infinity. I should have probably put the infinities over here for consistency. Because we can replace kv with k infinity anyway, right? The next term is going to have one of these kernels, another one of these kernels, and these minus I curly gv function. You realize that I'm already thinking about a partial wave basis. So this object is a matrix in the partial wave basis, Lm, L prime, M prime. And this object, in the same way, is a matrix in that basis. And this object is a multiplication of 3 Ks in that basis, such that the overall indices would match with the overall indices of the left-hand side, and so on. Okay. So then we have the next terms in the expansion. So I haven't written them down. So then the next thing that you do is to replace this GV function with the infinite volume plus the finite volume counterpart. This is the bit that I showed you in the previous slide. And this is the bit that is the infinite volume part. Okay. So GV can be replaced by infinite volume plus the corrections that are polynomial. They're from unshell pieces and up to all orders. Okay. So then let's try to reorganize this expansion into a bunch of different terms. Well, the first term is that I take the G infinity from all the terms that I have in this expansion. All right, so I have the kernel times IG infinity kernel, and so on, all with just G infinity. And if you think about it, this is nothing but the infinite volume amplitude, right? So the infinite volume amplitude already is derived from this simple realization that all these G infinities to all orders can come together to give this contribution. What about the next one? Well, the next one I can imagine to be when I only isolate one GV, not more. Out of all these terms, I get one delta GV. I forget about the rest. And then whatever is left before and after it, if you just think about it or just try to write it down a bit more explicitly, is I get a bunch of kernels times these G infinities in the left and the right. So I recover IM infinity from the left and right. Remember, all of these things that are coming next to delta GV are evaluated on shell, because delta GV is really defined on shell kinematics of the two particles. So then what about the next term? It's going to be when I isolate two of delta GVs from the full expansion up here, And that means that then I have isolated a bunch or an infinite series that would end up becoming IM infinity before, in between, and after. Okay, so that's really a nice reorganization. It will allow me to not only get this infinite volume bit, but also write everything in terms of finite volume function that is on shell and is connected to a bunch of other on-shell amplitudes, before, after, and in between, to all orders. So the next term is going to have 3 of these delta GVs and so on. So this is now a geometric sum. I can write it as IM 1 plus delta GV M infinity. All I have done is to take out IM infinity. Then I have 1 plus delta GV M infinity to some power, summed over. So then you just do the geometric sum. Or I can just write it as by multiplying by M inverse from the right. I can write this as I over M infinity inverse plus delta GV. Okay. So this amplitude that I was after now looks like something like this. It's very non-trivial to imagine that this would become like so, particularly given that we had to process this form and realize that this is unshell, and therefore would make all these amplitudes unshell and so on. But this is a final form. Okay. So why is this a useful form? Because now I can look at the singularities of this object, and those singularities are going to give me the poles or the energy eigenvalues associated with a finite volume calculation. Okay. And the reason that I'm doing this calculation in Minkowski is that the poles of this object is going to be similar to the poles of the Euclidean object, up to a very trivial analytic continuation, E to IE. Okay. So that's why just looking at the infinite volume case, the Minkowski case in a finite volume is sufficient. But in practice, we calculate these objects in Euclidean spacetime in lattice QCD. Therefore, we have to account, but nothing is different. Those energies are essentially the poles of the same object that I have here. Okay, so what are the poles of this object? It's actually given by this relation that I'm calling quantization condition. Okay, so let's make sense of this relation. Well, the poles are coming when the denominator is 0, but denominator is actually a matrix. Remember, these are matrices in partial wave basis. So the denominator is a matrix in infinite dimension, essentially, because this delta GV would mix all the partial waves, in fact, okay, which is a problem in practice. As we will see, there are some limits where we can still take advantage of this relation. And therefore, if it's a matrix, the singularity condition should be the determinant of that matrix being equal to 0. And it turned out that there are only a finite set of energies that would satisfy this condition. Not a continuous set of energies, but rather a finite set of energies. This is consistent with the fact that whenever you're in a finite volume with some boundary conditions, everything is discretized, right? There's no continuity. All the energies are discretized. It's just a property of finite volume in any setting. So, and I'm calling those E star n's to say that there are some set of n, E n star eigenvalues that would satisfy this relation. Not all energies would satisfy this, but only a set that is given by this. Okay. Okay, so that's our relation. It's called Lucher's quantization condition. Quantization because only a quantized set of energies would satisfy this relation. But other than that, this is really the most generic form. Okay. And by the way, I call this Lucher's formula, although Lucher's formula wasn't as general as this relation, because this delta GV function that I gave you in the previous page, this delta GV function that I gave you in the previous, let me see if I can rid of these. was very general. It was general in the sense that it applies to boosted frames, relativistic kinematics, non-zero or non-equal masses of the two particles. The Luscher's original papers were only considering scalar particles with the same mass in the rest frame, but then eventually the other generalizations came along. So this is like one of the most generic forms. And in fact, if you have spin-full particles, this form doesn't actually change, which is nice, because it really only depends on kinematics, not dynamics and other structures of the problem. Okay, so this is our Luscher's quantization condition. As I said, by itself, it's a pretty useless relation because it's a determinant condition over infinite dimensionality for these matrices, and it's not practical to get to solve these equations, right, if it's infinite dimensional. So we need some sort of truncation, and the truncation is acceptable, particularly at low energies, because we know that at low energies, only a finite set of partial waves would contribute to the amplitude. S wave is going to be dominant, maybe P wave, D wave, depending on the problem. And therefore, you can actually think about a truncation in the space of the partial waves, such that this delta GV function, you just take a sub piece of it that is relevant to the problem, and then you ignore these higher partial wave contributions. So you have to make sure that those are small contributions to the final answer. They usually are, okay? So this is now an example that it would be good for you to go through. Given the Luscher's quantization condition, we want to limit it to only S wave scattering. So we only have L equals 0, and therefore just M equal to 0 for both initial and final legs of our scattering amplitude, right? So it's going to be very simple. We're also going to assume M1 is equal to M2, and you're going to then show that Luscher's quantization condition would end up being the following simple relation. P star cotangent of delta of S wave, the phase shift in the S wave, as a function of P star, is equal to 4 pi C0 of P star squared. This is the function that I defined in one of the previous pages, the Luscher Z function or C function in this case. And P cotangent delta is just a usual P cotangent delta, the phase shift delta that you see in the expansion of the amplitude. The starting point for you should be to realize that the infinite volume scattering amplitude in terms of partial waves has the following form. It is diagonal in L and M bases. It has the following prefactor for this relativistic identical particle kinematics. And then it comes with e to the 2i delta minus 1 over 2i, just based on the fact that there's only a single channel and we have to have a unitary S matrix. This is the parameterization that you naturally would come up with. Okay, so if you start from this, put it in the Luscher's quantization condition, which is now only a single relation, there is no determinant. Go back to your delta GV definition over here and work out what it comes out of it once you have only L and M equal to 0 for these indices. And then you should be able to see that the relation would be simplified to a form like this. Okay, so this is called the S wave Luscher's quantization condition. This is the most commonly used quantization condition for applies a lot of times to these hadron scatterings in low energy, and therefore it would be good to drive it and to understand its implications. It would tell you if you give me a set of finite volume, in principle there is an N here, meaning that there is a set of these energies, then I have this known function, I can evaluate these known functions, and I get the value of the amplitude or phase shifts at the corresponding finite volume energies. Okay, so Luscher's quantization condition is not going to give you everything. It's going to just give you the amplitudes or phase shifts at the corresponding finite volume energies. Okay, so then you have to then think about how to generalize it to other energies. So you have to come with some sort of extrapolation or interpolation forms or parameterizations that is sensible and so on. But we'll talk a bit more about that in a few minutes. But that's the implication of the condition, that it is very powerful, it's completely model independent, with a few assumptions on the finite range of the interactions and the fact that we should be below the third particle production threshold, we come up with a fully generic relation that applies to essentially all 2-2-2 hadronic systems. Even beyond that, if you're interested in atomic collisions and so on in a finite volume, you can still apply this condition. So that's as powerful, because it doesn't make a lot of assumptions about the interactions, whether they're QCD interactions or they are atomic physics interactions with finite range. Okay, great. Okay, so the next topic is to extend this formula to 2-2 scattering with multiple channels. What does it mean to have multiple channels? It means multiple flavor channels. Let's imagine that you have pi scattering, but then you can imagine that your pi would go to kk, because that's an interaction that is also possible via a strong interaction. So you can have pi that mix into kk, pion mixes into kaon scattering. So you can imagine a scenario when your two pion states either go to themselves, they can go to two kaons, or they can, and then the two kaons can also go back to two pions, and this process can happen to all orders. Or you can have two kaons that go to themselves, or to two pions, or again back to themselves, and so on. So all of these processes are part of your scattering amplitude. So it turned out that even for these processes, there is a very simple way to generalize this Lucher's formalism. By just realizing that this infinite volume scattering amplitude is not just only a scattering amplitude in one channel, say A to A, but rather, in this case, a 2x2 scattering amplitude, where you also have off-diagonal bits, A to B and B to A, and then you have the B to B over here. So you treat everything together in this picture, okay? So this would account for the mixing between your flavor channels, and these guys are the ones that would have been there anyway, even if you didn't have the mixing between the two channels. Remember that these matrices are still matrices in partial wave bases. But they're also matrices in the flavor basis that I have written right here. If you have 3-to-3, if you have 3 coupled channels as opposed to 2, then this would have been a 3x3 matrix and so on. So you see the generalization. So that's for that. What about this delta GV function? Because not only we have the M infinity in the quantization condition, but we also have the delta GV function. So it is obviously going to have the following diagonal form, because this delta GV function doesn't know about interactions. It's just a kinematic function. If you go back to the derivation, it's just a kinematic function. All the informations about the flavors are in these K matrices, okay, these kernels. But the function itself, the delta GV, doesn't know anything about the kernels anymore. That's the bit that we identified. So essentially a diagonal matrix that would take you from A to A or B to B. This is just the two particle propagators in the S loop. So the two particles can only go to themselves, not to other channels, because that's just one propagation, one loop. So that has a diagonal base. Again, these delta GV functions are matrices in the partial wave bases, and they can have off-diagonal bits in the partial wave bases, but they have only diagonal bits in the flavor bases. Okay? And this discussion over here is essentially talking about the fact that rotational invariance is broken, therefore delta GV can have off-diagonal bits in angular momentum bases, but I already talked about that, so let's just skip this for the moment. So then how do you generalize your quantization condition to multiple flavor channels at the same time? That's the form. Well, you have a determinant over the channels, a determinant over the partial wave. You have a determinant over partial waves, and then you have the same relation, with the understanding that these M objects and delta GV objects are matrices in both partial waves and also the channel space. So that's as simple as that. And if you have multiple channels instead of 2, then the generalization is straightforward, obviously. Okay. So I have another discussion over here, which is good to remind you that I said that this M infinity function is diagonal in partial wave. And now we can ask, well, is it always true? Is it always true that in partial wave or angular momentum basis, we have a diagonal function? Well, in fact, no, because we talked about this before. For nucleon-nucleon channels, for example, if they're in a spin triplets, then we can have still the total angular momentum that is conserved in infinite volume. So in S equal to 1 channel, total angular momentum is conserved, but that means that you can have options for orbital angular momentum. For example, for NN channels in S equal to 1, spin triplet channels, we can mix L equal to 0 and L equal to 2, S wave and D wave, right? So the deuteron, for example, the deuteron wave function has contribution from both S wave and the D wave, okay? So in all these sort of spin triplet channels, we're in a situation where we can have mixings between these two partial waves. And depending on what the total J of the system is and what the parity of the system is, we can have mixing between different types of partial waves. So that means that this matrix over here may not necessarily be diagonal, right? So you can have off-diagonal bits, for example, corresponding to SD mixing in a spin triplet two nucleon channels. And the power of this quantization condition is that at the same time, it would enable you to not only fix the phase shifts of the corresponding finite volume energies, but also these mixing angles between different partial waves, like SD mixing. Also the mixing between different flavor channels, pi, KK mixing, and so on. So everything can, in principle, be constrained from this simple quantization condition that you see in this slide, okay? All right, so what's the next topic? The next topic is, what else can we learn from this quantization condition? Yeah, infinite volume amplitude is great at those corresponding energies. I have a model-independent first principle way to get access to these two particle scattering amplitudes from finite volume energies. But what else can we learn once we do that? So that's the next topic. I'm gonna talk about bounded states and resonances from this finite volume formalism. Okay, so in order to talk about that, let's forget about finite volume for a moment. Let's go back to infinite volume and remind ourselves what the analytic structure of a 2-to-2 scattering amplitude is, okay? You may remember this from your quantum mechanics course, like relativistic scattering in quantum mechanics. But let me just remind you that in general, a 2-to-2 scattering amplitude in the complex energy plane can have the following analytic structure. Well, it can have bounded state poles, meaning that if the E equal to 0 is the threshold, the E is the total energy. So like the threshold for producing the particles. So for 2-to-2 scattering, right? So the threshold is defined as you go with the same energy and you end up with the same energy, but your 2-to-2 particles can in principle have an energy that is less than twice the free particles, okay? And that's what the negative value is supposed to mean in this picture, that you can have a pole in the scattering amplitude that is associated with the bounded state energy, and it's on the negative real axis. And you may have multiple poles, but let's just forget about it and think about just a single pole, which is more common in nature. What else can you have? Well, you have a branch cut that is associated with the continuum of scattering states. Okay, so what does that mean? Well, I have two particles that are scattering, right? And then they, the energy and momentum are conserved. But in order for energy and momentum to be conserved, there are infinite number of possibilities to achieve that, right? Because we're in infinite volume. So there is a continuous amount of relative momenta that I can assign with the system such that I can still have viable scattering. So that's sort of the meaning of this. And if you just like go back to the definition of a scattering amplitude, so let me show you essentially this definition, okay? So if you write this M infinity as M infinity inverse, you get your P cotangent delta minus IP. At some point I wrote this in maybe a previous lecture, but P cotangent delta minus IP gives you your M infinity inverse. And once you have this minus IP, I think you, right, you can already see it from here. You have this IP, but in order to see it in the pole structure of the amplitude, you have to process this a bit farther. And this P is really sort of a square root of the energy, right? Or E star. And because you have this square root function, then you already know that there should be some branch points and branch cuts. If you work it out, it actually starts at what we call sort of the threshold for having this continuum of a scattering state. So what else can you have in this plane? Well, you can have complex poles as well. Poles that are in the complex plane, not just on the real axis, but also on the complex plane. So these are not really associated with the eigenvalues of QCD or your theory in infinite volume, but rather associated with resonances and some scattering channels, some amplification of your amplitude, if you think about it, right? So, and these complex poles can also be realized by looking at the analytic structure of the amplitude. For example, if you see something like a bright Wigner type of amplitude, you know that there's an associated pole, complex pole, and the imaginary part of that complex pole is related to essentially the width of that that resonance. Okay. So there's this sort of pretty rich complex structure of the amplitude in infinite volume. The question is, how do we get such a rich structure from finite volume physics? Because in a finite volume, you only have access to a discrete set of poles that are real valued. So I would have a bunch of things on the negative and positive real axis over here, but no branch points, no branch cuts, no complex poles. How do I actually recover something that is much richer than a bunch of real poles? Well, through the Lucer's quantization condition. Why? Because give me those set of real poles, I put it in this function, I evaluate M inverse at a bunch of real poles, real energies. Then I analytically continue the amplitude from E real to E complex. And I look at the pole structure or other analytic structure of that amplitude. So that requires not only a finite set of numbers for this amplitude, but rather a parameterization that would tell me what the functional form of this function is as a function of E, right? So you're back to the point where you don't have a full function, a continuous function of the variables to be able to perform analytic continuation. And therefore you have to rely on some parameterizations, which brings some sort of model dependence, but as long as you work with reasonable set of models, you work with a bunch of models so that they see they're consistent and assign a systematic uncertainty with them. By this few data points as an input for the value of scattering amplitude of those energies and those parameterization of the functional form of the amplitude as a function of energy, then you can have the full function, the full functional form. And therefore you can analytically continue it and look at the pole structure. So this is how we actually do this in reality, in practice. And this has been taken advantage of in many of the state-of-the-art calculations nowadays in Lattice QCD to be able to not only look at the bounded state poles, but also these resonance poles, because resonances are very common in QCD spectrum. We would like to understand them. We are exploring them in experiments like in Jefferson Lab and other facilities. And it would be really good to have first principle QCD determinations of these resonance properties. And we almost have it, because by first principle, we mean that we have access to the amplitudes of the set of energies. At that point, we have to look at the data and see how it looks. And if it looks like a bright Wigner, then that already tells you that you're dealing probably with a resonance situation. So you can use that bright Wigner form to parameterize your amplitude and get the information about the width and the mass of those resonances, which is, as I said, very common. Okay, the next thing that I'm gonna say is sort of the question of bounded state energies. It turned out that, so the complex structure we talked about, let's talk about the pole, because the pole can already be seen by doing a simple analytic continuation of the energy. So if the E star is K star squared over M, and I'm thinking about the non-relativistic setting, where by energy, I just mean energy minus twice the particle mass, and I'm assuming that higher order relativistic corrections are small. So energy or non-relativistic relative energy is really K squared over the mass of each of those particles. And let's imagine that the two particles have the same mass. Okay, so that's the energy. When we have a bounded state, that means that this E star is equal to some minus B and is a negative number. Okay, remember, this is already excluding the twice the mass of the particle because it's non-relativistic energy. Therefore, it's equal to the minus the binding energy in this notation. So then I can define a kappa squared, which is equal to minus K star squared. So kind of an analytic continuation from a real K star to an imaginary K star, such that the B is just K squared over M, or K, which I call it a binding momentum, is equal to a square root of M times B for this two particle system with mass M. Okay, so with this notation, you can go ahead and show that infinite volume binding momentum is the same as finite volume one. So there is in principle, this is infinity, all of these infinity, and this one is finite volume, is equal to the infinite volume counterpart up to corrections that are actually exponential in minus kappa L. And don't be surprised, this actually comes from Lucer's equation that is supposed to give you power law corrections. But as you see in this exercise, in situations where you have this polar structure, when you can actually analytically continue that Lucer's equation to the negative energies or imaginary momenta, you can solve it. You can process that sum, the Lucer's Z function, by looking at its polar structure, doing the Poisson resummation formula, and you're going to see that the first few corrections are going to look like e to the minus kappa L. Don't confuse this with e to the minus ml, m being the mass of, for example, pions in the theory. Those are much smaller than e to the minus kappa L in principle. Okay, so we have identified also exponential corrections to the binding energy of these objects. So is this intuitive? Did we expect this? Yes, indeed, because we're dealing with the bounded states. Bounded states have a localized wave function. The wave function goes like e to the minus kappa r being the relative distance between the two particles. So if I have a localized wave function, I know that it's not going to just see the boundary, right? Or its wave function is not going to be distorted too much by the boundary because it's already decaying exponentially. And that's really sort of the underlying reason for the corrections to be like e to the minus kappa L and higher. Okay. All right, so exercise 13 is asking you to start from the S-wave Lucer's quantization condition and try to derive the relation that I had in the previous page. If you need hints, check out this paper that I've given here for the derivation. But try to work it out first, and if you get the stock, then try to consult the reference. Okay, so we're almost done. I want to just mention in a couple of minutes a few other extensions and applications of the Lucer's formula. Lucer's formula really revolutionized lattice QCD field, because for a long time we've been so focused on single hadron properties from QCD, essentially because two hadron properties required S matrix calculations or scattering amplitude calculations. We didn't quite know how to do this in Euclidean space and related to the Minkowski space, but then Lucer's formalism would allow you to do this. And not only that, Lucer formalism has been generalized to 2-3 processes, 3-3 processes, and also to electroweak processes, for example. Okay. For example, if you have a decay of a kaon to the 2 pions, how do you calculate the scattering amplitude or transition amplitude associated with this decay from a Euclidean calculation? it's sort of a 3-point function calculation. Then again, in this process, these two pion states are asymptotic states in principle. And therefore, once we look at this process on a finite volume, we're dealing with back reactions of these pions, and we have to then define these amplitudes properly because they're initial or final states. In this case, the final state is non-trivial to define in a finite volume in terms of an asymptotic state. So we have to go through this sort of generalized Lucher's formalism, or the Luche-Lucher formalism, what is called, to be able to access these amplitudes as well. But the starting point is really to realizing that these two particle states below inelastic thresholds, or even the 3 particle states, once you generalize Lucher's to 3 particle states, have a particular dependence on the volume that have to be accounted for as we relate these finite and infinite volume amplitudes. Therefore, you can apply this formalism to things like PP fusion, it turned out, neutron disintegration in nuclear physics, or even just recently neutrinoless double beta decay amplitudes, which are a bit more non-trivial because they require non-local matrix elements of your electroweak currents. But even those situations have been dealt with at the moment. Okay. So what else remains to be done? Well, how if we are going to deal with 4 particle scatterings or 10 particle scattering? Unfortunately, pions are big problems in nuclear physics because their mass is very, very small. So as soon as you're dealing with processes that are of order of GeV in energies, that means that there is a possibility for creating not just 1 or 2, but multiple pions in either intermediate states or final states of your calculations. So if you want to do realistic high energy calculations in hadronic and nuclear physics, then you need formalisms that can go beyond 2 or 3 particle states. And this proven to be very hard. Even for 3 particle scattering, it took over a decade. For the formalism to be put together, it's pretty complicated and only recently been started to put into practice. But about 4 and 5 and 6 particles is their hope to go through the same technology and be able to relate scattering amplitudes to finite volume energies of these multi-nucleon systems. But one approach is to be a little less model independent and try to solve the corresponding effective field theories in a finite volume and connect the amplitudes. So that's one approach, but some people don't quite like it because they call it not quite first principle. It's just you assume some information about the short distance physics, your hadronic effective field theories, and then you try to constrain it with lattice QCD. But eventually that's all we've got, and it's better than just doing completely phenomenological approaches. So effective field theories are systematic. And as long as we have inputs, even if we don't have experimental input, if we can use our lattice QCD inputs for these energies and matrix elements in Euclidean finite volume calculations, we can match them to these effective field theory calculations with the same sort of conditions or settings, then that's better than nothing. Okay. But there are also these other post-Lucher's formalisms, I would call them. For example, I've given a reference over here that would rely on trying to really do this analytic continuation. So understanding Majorana and Tesla limitations better and trying to kind of change it by introducing some regulators that would have to be taken out of the picture very systematically as you take the infinite volume limit. But that requires an inverse problem, essentially, starting from Euclidean correlation functions in finite volume, and then try to analytically continue means that you have to perform actually an inverse problem, which turned out to be very difficult, as we talked about, with discrete set of points. It's very hard to do these inverse problems. There's been quite a lot of progress in trying to understand how to implement strategies like this, at least in simple problems. There are also other questions that remain unexplored. For example, finite volume corrections to light quantities. And what are the finite volume corrections to Hamiltonian simulation methods? And so on. Can we actually use some of these technologies that we've developed here and be able to apply it to problems when we just do Minkowski, but finite volume simulations of these scattering processes? So in other words, this is still a pretty active field of research. So if you are interested in this topic, it's a good time to get involved. Thank you.